My name is Temel. I will talk about our work, sound and automated verification of real-world RTL multipliers. This work is co-authored with my PhD advisor, Warren Hunt. Integer multipliers are one of the most fundamental components in processing units. They're used in CPUs, GPUs, custom signal processing systems, and so on. And they can be as large as 1000 by 1000 bits in certain applications, such as crypto processors. Multipliers can be designed with different methodologies. The most commonly used ones are Wallace trees and boost encoding. Depending on the application, these algorithms may yield very complex circuits. Given that multipliers are so common, their functional correctness is essential for systems reliability. Even though these design methodologies have been around for around 50 years, formal verification of multipliers is still a difficult problem. Existing methods either do not scale, require a lot of manual work, or they have a very limited applicability. We propose a different approach to verify multipliers. Our work is based on a simple term rewriting algorithm, and it is tested with more than 250 RTL designs, including isolated multipliers, multiply accumulate, dot product modules, designs with truncated, right-shifted, rounded, or saturated outputs. Our experiments have shown that our method is very fast and can verify 1000 by 1000 bit multipliers under 5 minutes, which is orders of magnitude faster than the other state-of-the-art tools. Additionally, we implemented this method on the ECL2 theorem prover and verified the soundness of the verification tool itself. I should note that this work is a continuation of our previous work that appeared in CAV 2020. We have made some improvements on the previous work to cover more embedded multiplier designs and achieve better proof time results. First, I will quickly review the integer multiplier architectures and how they might be used in other designs to understand the verification problem. Then I will review related work on multiplier verification. And in the third part of the presentation, I will describe the method proposed by this work. I will give the highlights of the term rewriting algorithm with a simple example. Finally, I will show experiment results comparing the performance of this method to the other state-of-the-art tools. An integer multiplier is a digital circuit that simply multiplies 2-bit vectors, which may represent signed or unsigned numbers. For example, assume that we have two vectors, a and b, each storing 3-bit 2's complement signed numbers. To create a partial product, we can sign extend these bit vectors by repeating their most significant bits. Then we can multiply each input bit with each other and create the partial products, as we would do for primary school multiplication. Our goal now is to sum all these partial products. We could sum everything column by column, going from right to left. Alternatively, we could add one row to the other, accumulating the sum to get the result. However, these methods are not efficient for a hardware implementation, as they may result in a large gate delay in our implementation area. Instead, we use Wallace tree and similar algorithms to sum these partial products. Wallace tree algorithm selects groups of 2 and 3 bits from the partial products, and it uses half and full adders to sum them in parallel. Then we reach a state where there are only 2 rows after these parallel additions. At that point, we can use an efficient vector adder, such as the carry look ahead adder, to calculate the final result. This summation technique provides a lot of parallelism, which reduces gate delay. We could achieve even better results by using different partial product generation algorithms, such as boost encoding and some sign extension tricks. These designs may also involve rounding, truncation, and/or saturation when returning the result. Integer multiply can have many use cases, including multiply accumulate, dot product, and floating point operations. Let's take a look at different ways to implement a multiply accumulate, aka MAC module. A MAC module aims to implement multiplication of 2 numbers added to a third operand. For example, the design on the left here uses an isolated multiplier to multiply 2 numbers, an additional vector adder that adds the third operand to the multiplication result. This design implements the desired functionality, but it uses 2 vector adders in the overall design, one here and one here. which gives a large propagation delay to the circuit. The design on the right implements MAC in a slightly different way to reduce gate delay. Instead of using a complete isolated multiplier, it uses a module that returns 2-bit vectors instead of 1. When these 2 vectors are summed, you will get this multiplication result. We take these 2 vectors and sum them with the third operand using a smaller Wallace tree and a final stage adder. Since this overall design uses only one final stage adder, it has better gate delay performance compared to the one on the left. Designers often implement such optimizations to improve the performance of the design, and these are very common optimizations. Unfortunately, for formula verification engineers, these optimizations make the verification process very complicated. If we have a tool that can only verify an isolated multiplier, we cannot use that tool to verify such optimized designs. There have been many studies and attempts to verify multipliers. However, these efforts mostly focused on isolated multipliers or multipliers with simple structures. Notable studies in recent years use the computer algebra method. These studies have reported much better results than the works published before. However, they reportedly do not perform really well on multipliers whose output is manipulated on the bit level, such as by truncating the output, and the studies on designs beyond isolated multipliers have been very limited. Additionally, a lot of these tools do not deliver any soundness guarantees. Because of these reasons, the efforts to verify multiplier designs in the industry have remained heavily manual. Verification engineers devise an often complex verification scheme suited for the design at hand. And they may have to come up with a new scheme every time a new design comes along or the existing design changes. Before describing our approach, let's take a look at what we are trying to prove. We have used the ACL2 theorem prover to develop our method and verify multiplier designs. As it is also a programming language, ACL2 lets users develop executable programs and provides the means to reason about them. ACL2 is also the theorem prover that is used in Centaur technology to verify really complex designs. Our target multiplier modules are RTL designs coded in a hardware description language such as System Verilog. We need to have a way to bring those designs into ACL2. We use the SVL system in ACL2 to do that. Then we state a correctness conjecture for a multiplier module as stated here. Def thumb is a commonly used event to tell ACL2 to prove conjectures. On the left-hand side, we have the symbolic simulation of the circuit for variables A and B. On the right-hand side, we see the specification. Users can change the specification to fit the design. For example, we can add another number to make it a specification for a multiply accumulate. Before we can prove such conjectures about multipliers, we first reason about the adder modules. For each distinct adder module, we prove that they can be rewritten with our functions that I will introduce in the next slides. When we start working on the main multiplier module, the adders are rewritten, and complex expressions for partial product generation and summation logic are formed. Our rewriting algorithm for multipliers simplifies such expressions to a fixed form. When the rewriter is finished with the left-hand side, it rewrites the right-hand side to the same final form. Then we compare the two sides with a simple syntactic check to conclude the correctness proofs. Let's go over these steps in more detail. The first step of our multiplier design proofs are creating rewrite rules for each of the adders that are instantiated in the multiplier. We do that by stating a similar conjecture for adders. Here we choose a specification for each adder module that is represented by our functions S and C. S stands for sum bit, and it is an alias for mod2. C stands for carry, and it is equivalent to floor of the y by 2. This table gives examples of these specs for some common adders. A half adder has 2 inputs and 2 outputs, and sum and carry bits can be represented this way: the sum output and carry output. The same goes for full adders, which have 3 inputs instead. Vector adders or final stage adders also have a fixed specification for each output bit, as seen here for the first 4 output bits. A multiplier might have different adder components, such as a 4-to-2 compressor. However, coming up with these specifications are often trivial, and we provide more examples in our documentations. Verifying the adders is a straightforward problem, so I will not discuss how we prove these conjectures about adders in this presentation. After the adder modules, we can now start verifying the multiplier module itself. This is the example conjecture that I have shown earlier. Our goal is to rewrite both sides of the equality into the same form and conclude our proofs with a simple syntactic comparison of both sides. An example of this final form for each output bit is given on this table. The least significant output bit, out0, is a summation of the first column of partial products, which is only one bit, A0, B0. The second output bit, out1, is mod2 of the summation of the second column, plus the carry from the previous column, and so on. This form is proved to be equivalent to the built-in. This form is proved to be equivalent to the built-in ACL2 multiplication function. Whenever we see a multiplication of 2 vectors, as given in this conjecture during our proofs, we rewrite the specification to this final form. So now let's go over the rewriting algorithm that can convert various multiplier designs, the left-hand side, to this final form. First, let's assume that we have a voluntary multiplier with simple partial products. After rewriting the adder modules with their specification from step 1, we may get this term at the top for multiplier output bit. Our goal is to simplify this term and convert it into our final form. This. We observe that such terms have many nested calls of the function s. We can get rid of such nested calls with this lemma. Basically, the arguments of the inner calls of s can be replaced with their arguments. After applying this lemma, we get a simplified term at the bottom. You can see that the arguments are simply extracted from the inner s instances. These are gone. These are replaced with these. This term still does not look like our final form, and we see summation of c's that have s's in their arguments. Since the final form does not contain such instances, they need to be simplified as well. And the lemma given here does that. When we rewrite the c term on the last line of the current term, this, the overall term simplifies to the term at the bottom. And we see that it matches the final form that I have shown you a couple of slides ago. Rewriting with these 2 simple lemmas helps simplify even very large multipliers. This example was for multipliers with simple partial products. If Booth encoding or some sign extension tricks are used, then we would see more complex expressions for partial products than we see here. We would have larger Boolean expressions instead of, say, A3B0, and to accommodate such terms, the theory is expanded with a few more lemmas to simplify those expressions and convert the overall term to the same final form. The idea is the same. Whenever a matching pattern occurs in the term, the lemmas are used to rewrite them. This happens automatically, so the user do not have to identify what kind of partial product generation algorithm is used. To keep the presentation simple, I'm omitting these lemmas here, and you may refer to the paper for further discussions. To summarize, first, the adder modules are represented in terms of s and c functions. This helps us generate expressions from a multiplier design with these s and c functions. And a handful of simple lemmas are used to simplify these expressions to a fixed final form. We can rewrite the specification to the same final form and conclude the multiplier correctness proofs. This method works for isolated multipliers, multiply accumulate, and dot product designs, and so on. It also works when the output is rounded, saturated, truncated, right-shifted, or even bit-masked. In cases where two sides do not match syntactically, we also developed a system to send the simplified terms to a set solver so that we can quickly generate counterexamples, or maybe even have set solver finish the proofs for us. As I mentioned earlier, there are many studies on multiply verification. We selected the two of them that perform the best. One is from Mahsun and others, whose work was published in DAC 2019. The other is Kafmun and others, whose work was published in FMCAD 2019. Both of them have made significant improvements over the works published before them, and they have continued to make further improvements in their tool ever since. Monsoon's tool can be considered fast when compared to the work that came before, but they're still slow, their tool is not verified, and they do not provide certificates to validate the proofs. Kaufman's work is published some time later, the same year, and it is much faster, and they can produce certificates after they verify a multiplier, so the proofs can be validated by an external tool. Despite these tools being the fastest available tools out there, they still do not scale well for some designs. This table delivers average proof time results for various different isolated multiplier architectures. These include multipliers with signed or unsigned simple partial products, or signed or unsigned Booth encoding. For the summation trees, our tests include array, wallet tree, data tree, 42 compressor trees, overturned stage trees, and so on. For the final stage adders, these benchmarks include various parallel prefix adders, such as Brett-Kung and Ladner-Fisher, and many more. Mason's tool failed to verify a good portion of the large multipliers by timing out. Kaufman's tool is more applicable to more designs, and even though it missed some, it could verify a lot more. However, it started timing out more for larger Booth encoding multipliers. That is why the average timing results for 512 by 512 bit multipliers seem faster than 256 by 256 bit multipliers. On the other hand, we see that the tool we developed can verify all the designs, and it is orders of magnitude faster for large designs. These numbers are for isolated multiplier designs. We have experimented many more designs types such as multiply accumulate, dot product, multipliers with control logic, multipliers with arbitrary input operand sizes, and multipliers whose output is truncated, right-shifted, or rounded. Our tool can verify all such designs automatically. To use our tool, the only thing that the user needs to do is verify adder modules and decide on a specification for the main module that includes multiplication. We could not find any publicly available tool that can verify such complex designs. The other tools are programmed only for n by n bit isolated multipliers. Kaufman's tool recognizes n by n bit unsigned multipliers whose output is truncated at the first n bit, but in our test it failed to verify truncated multipliers. In addition to publicly available benchmarks, I have used our tool to verify multiplier designs developed in Centaur technology. In addition to various x86 integer multiplication instructions, our tool is also used in the verification flow of a floating point multiplication, such as an FMA. In short, the method and the tool I have described today is much faster, and it is applicable to many more design types, not to mention that it is completely verified, making it a reliable verification method. In short, we created this term rewriting algorithm that is based on a few simple lemmas. Many different multiplier designs are efficiently and soundly rewritten using the theorem proving system ACL2. As verification of multipliers is a famous problem, there have been many studies trying to solve it. Almost every year something new comes out, and in recent years there have been substantial progress. Still, these methods have had important restrictions that limited their applicability. The method I described today and the verification tool that we have developed provides much better results. It can verify large multipliers very quickly, For example, 1000 by 1000 multipliers are verified under 5 minutes. It applies a large variety of design methodologies and arithmetic operations. And very importantly, the program itself is verified so that the user can trust when the design is claimed correct, that it is indeed correct. We have also had the opportunity to test this tool for designs in Centaur technology, and we have been able to integrate our tool in the verification flow to be used for real-world designs. The approach we have taken may be considered a bit distinctive. Verification based on term rewriting is not new, but making it work successfully and highly competitively at this scale is not very common. We hope to develop and see similar verification methodologies applied to other arithmetic circuits or verification problems as well. Thank you very much for listening.